Welcome to a lesson with Dr. Powell. Let's take a look at an example of a surface integral. We're going to integrate vector field over this surface. Parabolic bowl, and we'll go up to a height of 4. And let's take a really simple vector field, namely just 1, 1, 1. Okay, so to integrate this, we are going to get a differential 1 form with our components of our vector field. 1, 1, 1. And now for the x component, we think what's opposite x is y and z, and the order is y, z for counterclockwise order to be right. For x, there's a, or y right here, there's x and z, but to be counterclockwise properly, we're going to be dz, dx. Okay, and then over here, this is just dx, dy. So the right order, if you think about the counterclockwise order of things. So x, y, z, zx is the right order, xy is the right order, yz is the right order. Okay, so we got that, and then we're integrating this. All right, but we're going to be doing on the surface. Now, how do we account for that surface? Well, it has to do with z is a function of x and y. And we can think of its derivative as, well, let's take the derivative, the gradient, 2x, 2y. And let's see, for the input, or the kind of like the input changes, let's suppose we have dx and dy. So for this amount of run, what's the rise? Well, the rise is going to be how much z rises, right? How much x rises, how much y rises. So the run of x and y put in here gives you the rise of this, which is the rise of z, since this is the derivative of z. Okay, so this is a dot product. And we get that dz is equal to 2x dx plus 2y dy. We use this and just replace the dz's that we find with that expression. So we end up getting 1 dy wedge with 2x dx plus 2y dy. That's for the first part right there. Okay, the next part, and we'll just kind of say this plus, okay, this part right here is going to be 1, and then we have that. So 2x dx plus 2y dy wedge dx. All right, now we have the next part, plus 1 dx dy. Notice what's happening. We're getting dx's and dy's grouped together. It's kind of nice. Notice something else. Okay, this wedge product, which is like kind of like an area type property, because you're kind of putting two things together like a dy and dx. If you put a dy and a dy together, you don't get any area at all. So as this distributes, we just ignore that part over here, because there's a dy put with the dy. Here, distributing the dx wedge over here, same thing here. So if you see a double count, that doesn't give you area. And really, this is a surface, an integral, and we're kind of doing things with respect to areas on the different projections. So this is area time. Okay, so then we put, so the wedge, notice we have dy wedge dx. Now, order is very important here because it kind of represents how we're viewing the area, from the top or the bottom, from one side of it or the other side. Notice how you have the order of dy wedge with dx right here. That's the wrong order. So we switch the order and put a negative on right here. So this guy right here turns into -1. Oh, that's right. Let's see here. So -1 times, and then we have a 2x. Okay, so maybe we'll just do that. Okay, so -2x, so 1 times 2x, but then we make it negative, and dx dy. This part right here, notice also, oh, yet again, we have a dy dx, and it's this one also is negative. It's the wrong order. So we'll put a negative on as well. -2y dx dy. And then here, this is just what it is. All right, so everything's in terms of dx dy. Now we can just factor out the dx dy, and we have a regular integral with dx, and we can drop the wedge since we've already done all the area orientation that we need. So then we end up just being able to write out a double integral, and we have so negative 2x minus 2y plus 1, and that's all with the dx dy. All right, now integrating over this would be so much better if it was in polar coordinates because we're kind of integrating over a, so dx dy, notice we've eliminated the z completely. We've just kind of dropped everything to dx dy calculation. And that's kind of what we do when we kind of replace our dz with things in terms of dx dys. We kind of take this thing that's kind of happening three-dimensionally and push it down to something that's very two-dimensional. So, and notice where it pushes down. This region that it pushes down to is a circle. It'd be nice to do that in polar coordinates, right? And what's its radius coming out to here? Let's see. Well, here this should be, r should just be 2, right? If we think about that, because, you know, we're going up to 4, so 4 is equal to x squared plus y squared. Take the square root of x squared plus y squared, square root of 4. And the square root of x squared plus y squared is equal to r. So r is going from 0 to 2, and theta is wrapping all the way around 0 to 2 pi. So we can write 0 to 2 pi. R is going from 0 to 2. We have negative 2x minus 2y plus 1. But now we need the conversion factor because we're doing polar. So r dr d theta. Oh, we also should change that, shouldn't we? Yeah, let's go ahead and change that up. Replace x with r cosine theta. Replace y with r sine theta. So let's go ahead and do that in our calculation here, and we'll get this surface integral under control. Okay, so we got 0 to pi, 0 to 2, we have negative 2r cosine theta minus 2r sine theta, and then plus 1. But then let's multiply, okay, let's multiply this r into everything. So r squared, r squared. Okay. Let's see, and should we do dr? Yeah, we're doing r first. Okay. R and then d theta. Okay. Great. So then we integrate, take an derivative with respect to r. So we get negative 2/3 r cubed minus 2/3 r cubed. Okay, but then we need times cosine. Sorry. I'll just put the cosine here. Or maybe I'll just rewrite it here. Let's just rewrite that because I didn't get it written out. Okay, so minus 2/3 r cubed cosine theta, then minus 2/3. You know what? We can actually factor out that that negative 2r squared. And then this is just a constant cosine theta plus sine theta. So let me just do that here. Okay, so that's just a constant factored out, and then we're just taking an antiderivative of negative 2r squared. All right, then here that's just plus r squared over 2, and we go from 0 to 2. All right, so we just plug in 2, and we end up getting negative. Okay, here when we plug in 0 for r, we're just going to 0 overall, right? Double check. Okay. Plug in 2 right here, that's 8 times 2 is negative 16. Negative 16/3 times cosine theta plus sine theta. And then we have right here, it looks like we plug in a 2, we get 2, right? Because 2 squared over 2 is just 2. So plus 2, and plugging in 0 is 0. So this is the result of just the r calculation. Then the theta in it calculation, we integrate with respect to theta as we go from 0 to 2 pi. Notice that cover a complete period here and here. Okay. So the integral over here is just 0 because 0 to 2 pi integral of cosine or sine is just 0. So we just have this. So we just have 2 popping out right now, but then we take an integral of that to theta, go from 0 to 2 pi, and it looks like we're sitting at 4 pi. So this this surface integral integrates to, yeah, it integrates to 4 pi. Thanks for watching.